Okay, so we are talking about one-dimensional motion, kinematics in one dimension, and we said that to describe the motion in one dimension, we have to identify a reference frame. And since it's one dimension, I just need a straight line. And so, for example, if the motion is horizontal, here we are. Here I have my reference frame. So I'll choose an origin and I will choose a side to be right and another one to be left, or to be east or west. And instead of using these two words, east and west or right and left, what we usually do is to associate with that motion a sign. So instead of east here, I'll be calling plus. Instead of west, I'll be calling minus. Same thing if this motion is in the vertical. It's still a straight line. I'll have an origin and I will define what is up and down. And I can associate with up and down a sign, either plus or minus. Okay, so this plus and minus does not mean more or less, just defines the direction which we'll need to say what is the direction of the motion. Okay, other things that we defined. We talked about distance, right? We said the distance is just how much the object traveled. And we said the distance is a scalar, it's just a number, and it's a number, of course, with units. Then we talked about displacement. Then displacement, let me write here, displacement is not just how much the object traveled, but how far away it went from its starting point. And the displacement is a vector, and this is very important because a vector comes with magnitude and also with direction. Okay, associated with distance, we talked about the average speed, and the average speed is just the ratio between the distance and the time elapsed to cover that distance. In the international systems, the units used for distance is meters, for time is second, and so for average speed is meters per second. Okay, associated with displacement, we define the quantity which is the average velocity. And the average velocity is the ratio of the displacement divided by the time elapsed. What is this displacement? The final position minus the initial position, right? And the units again is meters per second in the international system. But remember that displacement is a vector, has magnitude and direction, so average velocity also is a vector, has magnitude and direction. All right. We also talked about the instantaneous speed, and we talked about the instantaneous velocity, which we just decided that we would call just velocity instead of using the whole term instantaneous velocity. And what is the instantaneous velocity? This ratio, but when the time interval is very, very small, infinitesimally small. And okay, here we also have the instantaneous speed, which we can just talk about as speed. So the speed is what we read in the speedometer of the car, and the instantaneous magnitude of the velocity. All right, and later we also talked about acceleration. If the velocity changes, then we can define an average acceleration, which is the change in velocity in the time. And similar to instantaneous velocity, we can also define an instantaneous acceleration, which is that ratio, but when the time interval is extremely small, right? Okay, how about the units? The units for acceleration. Well, velocity is meters per second, time is second, and so we have meters per second squared. All right, displacement is a vector. average velocity and velocity also vectors, and therefore acceleration also a vector. So it comes with magnitude and direction. Okay, very important point that we said. If we get an acceleration that is negative, that does not necessarily mean that we are slowing down. Negative acceleration to be slowing down only if well, let me try to say it better. No? What we decided, what we understood is we slow down only when the direction of the acceleration is opposite to the direction of the velocity. If they are in the same direction, then the speed, the magnitude of the velocity increases. No? So acceleration, velocity in the same direction, we are accelerating, our speed is increasing. Opposite direction, then we'll be slowing down. No? And this sign may be plus or minus. And the minus does not mean that we are just decreasing the speed. No? If, let's say, A is red, okay, and A is pointing in the left direction, which I'm calling negative. So if my A is in a negative direction, and if my velocity is also in a negative direction, well, what will happen is the magnitude of that velocity will increase. So that minus does not mean less, it only means the direction. Very well, so let's come back to what is new. So here we are talking about, as we said, we have a reference frame, we are talking about horizontal motion, we define our origin, and we define what is positive direction and what is negative direction. Here we have the average velocity, which is the displacement over time, and as we said, the direction of the average velocity is always the same as the direction of the displacement. If the displacement is towards the east, positive displacement, the velocity is positive. If we are moving in the negative direction, then my velocity is in the negative direction. Okay, if the velocity is constant, if the velocity does not change, if the velocity is uniform, then for sure the average velocity and the instantaneous velocity are the same, right? It's not changing, it's constant velocity. What can we do with that? Well, remember what we said, right? The average velocity is the displacement divided by delta t. So we can write this expression as final position minus initial position divided by delta t. And what we usually do is, instead of calling it x2 and x1, we call the final just x and the initial x naught. Okay? And usually the initial time, we set it equal to 0. We start our chronometer when our motion starts. So the final time we call just t, and the initial time we just set it to 0. So with this equation here, which is just the definition of the average velocity, I can rearrange it and get the following. Okay, so just from the definition of average velocity, I can rearrange it. Well, we know that the average velocity does not change, so average and instantaneous is the same. So that's why here we are just calling it v. The final position we are calling x. The initial position we are calling x naught. And the change in time is t, because the initial was just 0. Okay, so starting from that, I can multiply v by t. So I'm rearranging this equation. And then you can see that I can write that the final position is going to be equal to the initial position, now I put this on this side, plus vt. So these two are exactly the same equation, okay? They are equal, but they're just a rearrangement. There are two different ways to write the same thing. And this is when the velocity does not change when we have uniform velocity. Alright? Okay, so let's see what is next. The other scenario, so this is one kind of motion when we have uniform velocity. But we could also have a change in velocity, change in the instantaneous velocity. So when the velocity changes, then we do have acceleration. And the average acceleration is the change in velocity divided by time. Now, so this is the other definition that we talked about. And what do we know? Well, acceleration is also a vector, but the direction of the acceleration does not have to be the same as the direction of the velocity. If it is, that means that the velocity will be increasing. Okay, so if the direction of the acceleration, the direction of the velocity is the same, the magnitude of the velocity will be increasing. But if the acceleration and the velocity have opposite directions, then the magnitude of the velocity will be decreasing. Alright? Okay. Now, what we will be studying here in this chapter and in the following ones are cases in which we do have acceleration, but the acceleration does not change. Uniform acceleration, constant acceleration. So, the instantaneous and the average, remember we put a bar for the average, the instantaneous and the average are just the same. Okay, in a case like this, where we do have acceleration but it is constant, what can we say about the velocity? Well, the velocity is not going to be constant, because if there is acceleration, the velocity does change. No? So if the velocity does change, instantaneous cannot be equal to the average. Alright? Okay, so let's see what else we'll be getting here. So we'll be studying this scenario where the acceleration is constant, and now we want to talk about the equations that we can use. Okay, so the first equation that we'll be talking about is this one. So let's try to understand what we are writing there. Remember what is the definition of acceleration. So definition of acceleration, we'll write it again here. The average acceleration is the change in velocity divided by time. And if this acceleration is constant, then the average acceleration is just a, does not change. Average and instantaneous is the same. Okay, so I'm going to be rewriting this equation as a, because instantaneous and average is the same, is equal to the change in velocity, which we were writing as final minus initial, and final time minus initial. Let me do the same thing that we did when we were writing that expression for velocity. What I'll do now is, I'll say that final velocity, I'll just call it v. And initial velocity, I'll just call it v naught. Final time, I'll just call it t. And initial time, I'll say it's 0. So that's what we are getting there. Now, rearranging this, we will find that at is equal to v minus v naught, which we can then write as v is equal to v naught, I put on this side, plus at. So you see that this equation for velocity, this equation for acceleration, they are the same equation, just written in a slightly different way. Alright? Average acceleration is equal to instantaneous, because what we have here is uniform acceleration. So this is also one kind of motion that we'll be studying in this chapter. Okay? Alright, so what we can say is that the velocity is linear in time. Linear in time means time here is to the power of 1. Alright? This means that if I write a plot, and this is what this is saying here, if I write a plot of the velocity versus time, in a case where the acceleration is uniform, where the acceleration does not change, where the average and the instantaneous is the same, I just get in this plot a straight line. The slope of this plot gives us the value of that acceleration. Alright? Alright. We see other equations showing up here, which we will need when the motion is, when the acceleration is constant. So what are the other expressions? Look at this one. What we are saying is that when the velocity changes, but with a constant rate, as in this case where the acceleration is constant, when the velocity changes with this constant rate, then the average velocity is the middle point between the initial and the final. Okay, so basically what we are saying is that suppose I had a motion from time 0 to a certain time, 10 seconds for example. Okay, time 0, my initial velocity, let's say, was 0. Time 10, let's say my final velocity, let's give a value for it, was 200 meters per second. Okay. What is the average velocity? Well, half of my trip, okay, half of my trip in my first 5 seconds, I moved with a velocity that was less than this middle point, less than this middle point, and half of my trip I moved with a velocity that was more than this middle point. So what is the half? What is the midpoint there? Well, the midpoint is just the v naught plus v divided by 2. So the average velocity in the scenario where the velocity change at a constant rate is just initial plus final divided by 2. So in this particular case, the midway, the average velocity would be just what? Between 0 and 200, it would be just 100. Alright, so this is what this equation is saying. Okay, another important equation, this one. Okay, so this is an equation for velocity. This one in red is an equation for position. How do we get that equation? It's a little game. You do not need to know how to derive it. Okay, you just need to know how to use it. But I'll just show to you quickly here. But again, you do not need to know how to derive it. Okay, but how do things start? I'm going to start from that equation that we had, that definition that we had for the average velocity. Average velocity is final position minus initial position divided by time. Alright? Okay. We just said that the average velocity, in this case where the velocity does change, the average velocity is that midpoint, is the initial velocity, the final velocity divided by 2. Okay? So what I'm going to do is I'm going to substitute this equation with this. Okay, so here where you have this average velocity, I'm going to put this equation. Alright, so then I have v naught plus v divided by 2 is equal to x minus x naught divided by t. Let me rearrange these things. Okay, so I'm going to multiply these guys by t. Okay, and what are we going to have? I will have the x is equal to x naught, and then v naught t divided by 2 plus v t divided by 2. Okay, so what I did is I multiply these two terms by t. That's what you're seeing here, v naught t over 2, v t over 2, and what was remaining here, the x naught, I put the x naught on that other side. That's not all. Here I have an equation that involves the initial conditions, the initial position, the initial velocity, and the final velocity. Well, but we just found here an equation for the final velocity together with the acceleration. So what I'm going to do now is I'm going to continue with this. X equals to x naught plus v naught t over 2. And now instead of the final velocity, I'm going to put this equation here. So then I have v naught t over 2, because I put the v naught here, but I don't have just v naught, I also have at. So if I put at here, I have at, there is another t, so this becomes squared divided by 2. And then you can finally see we get x is equals to x naught plus v naught t plus a over 2 t squared. and this is that equation there. Okay, so we found that equation. So you see that the equation for the velocity when the acceleration is constant is linear in time, while the equation for position, the final position, when the acceleration is constant, is quadratic in time. So if I have to make a plot of position versus time, I get a parabola, because the parabola is when we have a quadratic dependence, in this case quadratic in time. Alright, but you see that there is one last equation which involves again velocity, but if you look carefully at this equation you don't see any time showing up. So here we have time, here we have time, but here there is no time. It's an equation that involves only the velocities, the positions, and the acceleration. How do I get that? Well, this equation is nothing new, okay? I get this equation just by combining these two equations, that's it. Okay? I get this equation just by eliminating the time from these equations, these two equations above. So let me just show to you how we do that. Again, you don't need to know how to derive, you just need to know how to use the equation. If you don't remember this one, well, then be sure you remember this two, because then you can derive that one, okay? Or you just make sure you do remember it, okay? So let's start again from the equation, well, the definition for from the average velocity that we had, okay? And so the definition for the average velocity, again the same story, final position minus initial divided by time. So we can rewrite it like this. So position is equal to x naught plus average velocity multiplied by time. Okay, but as we said, this average velocity is that midpoint, so I can write as v naught plus v divided by 2 multiplied by t. So we did this already when we were trying to obtain this equation, right? There is so far nothing different from what we are doing there. But look, now what I want to do is I want to get rid of time. Okay, I want to get rid of time in this equation for position. So what I'm going to do is I arrived at this point, and I'm going to use the other equation that I have for velocity to get rid of time. I'm going to substitute this time with this equation. So what I'm trying to tell you is I want to get rid of this time. I have this equation, so I'm going to rewrite this equation for velocity as v minus v naught is equal to at, which I can rewrite as t is equal to v minus v naught divided by a. So you see I'm isolating the time. I'm isolating the time, and then I'll put this into this equation. So now I have x is equal to x naught plus v naught plus v divided by 2, and time is this one, which I can write as v minus v naught divided by a. Okay, if you look at this, I can rewrite this in a way that may look more familiar. Instead of v naught plus v, I'm going to write it as v plus v naught. Okay, so what do you see here? That I have v plus v naught multiplied by v minus v naught, and this is simply v squared minus v naught squared. Now you must have learned this before. And in the denominator I have 2a. Alright, so now things are getting very similar to this expression. Let me play a little bit more with that. So I have here v naught minus v naught, v squared minus v naught squared, 2a, okay, is equal to x minus x naught. And I can multiply and divide by 2a. So I can put this 2a on the other side, so 2a here. And then we have the expression v squared is equal to v naught squared plus 2a x minus x naught. And then finally we arrived at other equation. Okay, so these are the 3 or 4 important equations that we'll be using a lot. The equation for the velocity as a function of time. The equation of position as a function of time. This is linear in time, this is quadratic in time. And here we have an equation where time does not appear. So if we have to solve a problem where time does not appear, this is a good alternative. Okay? And here is just a simple equation that came from the fact that the velocity changes at a constant rate. So this is a main point of classical mechanics. No? If we give the initial conditions, that is, if you give the initial position, the initial velocity, we can predict the future. We can say what is going to be the final velocity of the particle, what will be the final position of the particle, and so on. Alright, so we already talked about the plots, and now let's try to solve problems. Okay, we are going to put all of these equations together to try to solve this problem. So let's see how we are going to do that. Alright, so first question. How long does it take a car to cross 36-mile wide intersection after the light turns green if the car accelerates from rest at a constant acceleration of 2 meters per second squared? What are the important information that we have? Okay, we have that the displacement, the distance that we want to travel here is 36 meters. Okay, so the magnitude of the displacement that the car has to cover is 36 meters. Okay. Also, we know that the car accelerates from rest to a certain velocity, right? So from rest is an important information which tells us that the initial velocity is 0. And we know what is the acceleration, is constant acceleration, and it is 2 meters per second square. So you can choose a reference frame, it doesn't matter so much now, but let's see what is the question. Now, how long does it take for the car to cross? How long is a question that involves time. So I'm not going to use the last one that we showed, but let's see if we could use, for example, that equation that involves position, which was x is equal to x naught plus v naught t plus a over 2t squared. Let's think, is this a good equation? Well, x minus x naught I can write like this. X minus x naught is how much we have to travel. It's 36, so I have this information. This looks good. V naught multiplied by t. Well, v naught is 0, so I don't need that. And a we do have. A they told us is 2. So 2 divided by 2. And well, this looks like a good alternative. So here I have t squared is equal to 36. Right? So we have to do the square root, and then t, if you do the square root, you get t plus 6 seconds, or you also get t equal to minus 6 seconds. Mathematically, both answers would be fine, but physically, no. Physically, the negative does not make sense. Time does not go backwards. Okay. All right, so let's see now the second question. So let's erase this one. And the second question is, let's try to design an airport for small planes. Okay. And the plane that we are going to use there must reach 30 meters per second. So the final speed has to be 30 meters per second, otherwise the plane cannot take off. And we know that the power of this engine is such that the plane can accelerate with this acceleration 4.50 meters per second square. Okay, and well, it's going to start accelerating from 0, right? So this is our initial velocity. And the first question is, if this runway is 81 meters long, can the plane reach the required speed for takeoff? Well, let's see. See, we have no information here about time. So the best way to go is to use that equation where time does not appear. V squared is equal to V naught squared plus 2a delta x. Alright? Okay, if delta x is 81, now that's the size of the runaway, are we going to reach a speed that is at least equal to 30 or more than 30, so that guarantees that the plane will be able to take off or not? Well, let's put these numbers into the equation. Let's find what is the V naught, what is the V that we are going to find for these 81 meters. So V naught is 0, I'm not going to write anything. I have 2 multiplied by 4.5, which is 9, right? And 9 multiplied by 81. If you do this problem, find the square root of V, you will see that V is going to be 27 meters per second. Well, then we are in trouble, right? We are not reaching the 30 meters per second that we need, so the answer is no. Now we will not be able to take off. So 81 meters is not enough. Okay, so comes now the next question. If this is not enough, what is the minimum length that we need? Well, the minimum length is the one that will give us those 30 meters per second, right? So needs to give us the 30 meters per second. The initial is 0, so I'm not going to write. The acceleration does not change, is that always for the same planes. 2 multiplied by that acceleration give us 9, and from here you will find what is the delta x that we need, and you will see that the delta x is 100 meters. Alright, so we are done with this problem, and then we move on to the next topic, which is freefall. Okay, and freefall will be the topic for the next movie.